family as the first nodal officer. Most importantly, he is a fellow of Royal Society of Case. So, I would like to request Professor Mondal to start with your presentation.
Thank you, this opportunity of telling of you. There's a background coming.
You please mute your audio. Yes.
I was there in your college on January 4th last time, and I have seen the bigger outreach research as well as teaching going on compared to our time. And today, I first want to thank Prashanto and Vikasda for their invitation, and the Principal Maharaj who has been there for some time and met him last time also. Before I start my presentation, I want to show you, you can see on the back side here, a wooden statue of Swami Vivekananda that is there in my office. When I visited Nagpur facility of Mission, the Principal Maharaj gave me that one. So with his inspiration throughout my life, I have been doing okay. And as you have heard that I'm doing this lithography for over 36 years now. My first training was a Cotton's lab who had 3 refractometers, single crystal refractometers of his own. And department had only one for his other faculty, about 70 of them. So I have handled all 3 refractometers, and the training in USA was such that you have to maintain the instruments. So I carried that here, established the facility. I'll show you part of it. What is order, and the application most importantly in the pharmaceutical industry. And you'll find out that the measurements for these 2 techniques deal with the solid samples. So I will give you some background on solid materials. And those who are in first year, you'll see that this type of things that you will be studying at this time, whether you are taking chemistry course or a physics course. Now, it's a technique. That means when we make some material, we want to understand their crystallinity, understand their theorems of structures. And so therefore, if I want to tell you that for any measurement, we have material and I want to know some basic properties, what you need to have? You need to have a source and your sample, and the interaction between source and sample would generate some signal which is detected by a detector, and we analyze that signal to understand what kind of information we get. However, the interaction of source and sample have to be compatible in the sense that for what reason we are doing this kind of measurement, and the detector also has to detect that. So with this philosophy for any measurement, let's go back to the subject, that is X-ray crystallography. So therefore here we have samples like single crystal or powder. Powder is nothing but multi-crystalline material. That means it is not a single crystal, it is bunch of single crystals that are together. Just like when you crystallize some organic compound, you get hundreds of crystals, and that is the powder samples we are talking about. And in this case, to understand the theorems of structure or some other information in a minute you will see, we interact with the X-rays. That means my source is X-ray. What is the reason? Because our interest is to know the bond distance and angles so that we know the theorems of structures. And as you know that these bond distances are in the angstrom. For example, a carbon-carbon single bond is 1.54 angstrom. Therefore, my source should be having wavelength in the angstrom region, and X-ray happens to have that. That's why we use X-ray. And of course, to detect that interaction, which we call diffraction, we use a detector. And then a lot of mathematics is involved to give you the information. So today we are going to deal with a lot of different things. Here with me, I hope you have the patience for 75 to 80 minutes. I teach a course for both semester on this subject. So I will be very careful with two things. One, not to go over too much because audience is in first year mostly. And second is that I have to compress a lot of material in this short lecture, which I gave 6 to 7 parts. So here is the difference between of the single crystal and powder. As I said, in single crystal you have one single crystal, the incident beam X-ray interacts with it and it diffracts to give you the signal that will be detected by the detector. But in powder, what happens, as I mentioned, you have multiple single crystals, but those which are colored in blue, that are interacting with the X-ray instant beam and gives you diffracted beam. Note that if this blue also interacts with X-ray beam, but it goes other way, not towards the detector, we cannot get this also. So we are interested to see how this is manipulated by rotating the sample and many other stuff. Right? Now, what do we get in single crystal versus powder? In single crystal, we get the diffraction pattern that are designated here as the white dots. Okay? And so it happens to be a 3D information. But in powder, what we get intensity versus the 2 theta plot where we have this signal. We'll discuss about this in detail. But here you have the powder in 1D. That means single crystal is more informative, powder is less informative, but you find out that getting single crystal is difficult and all the time you don't need single crystal structure. On the other hand, powder diffraction has been the gold standard for pharmaceutical industry. Okay. Now, in a short one slide, I can tell you what is going on in single crystal diffraction. For example, you have a X-ray beam generator that can be rotating anode or steel tube, and that goes to some kind of optics like mirrors or monochromator, and then some focusing beam, and it gives you that incident beam where the crystal interacts and there is a detector. Then it has to be processed and you get a structure. And because of this diffractor, which of in a minute, it can be pulsar Eulerian or kappa geometry. Nowadays there is no Eulerian or kappa. So what I want to tell you that you give a crystal to somebody and due to this measurement you get a structure here with a lot of mathematical involvement. So you would say, wow, that is very nice. My crystal having this structure, what is the time frame and all those will also mention. Right? On the other hand, in powder, we actually measure the intensity versus 2 theta as I showed you earlier like this, and then we have the interest to give the HCl value with respect to D. D is that 2d sin theta in Bragg's law, we'll talk. And here you notice that it is a second bracket. That second bracket shows that it's a family of planes, not a single plane. That is because of the limitation of order diffraction that we don't have a single crystal giving you the deflection, which is represented by parenthesis. Okay, so this is the difference. So if you have this information, then you say that, wow, I already know what is single crystal and what is powder. I left this as blank to tell that the last 4-5 slides is kind of a summary to tell what is involved. But that doesn't mean you learn much. Now I start the details of what is involved in this. Okay? Now as I mentioned that we need to talk about solids because we deal with the solid sample. And here I have chosen the classification of crystalline solids. There are molecular in nature, there are ionic in nature, they can be metallic in nature, they can be covalent in nature. So these are the things. And this particular topic, next 5 to 6 slides or more, is the subject of solid state physics or chemistry. I hope hope these slides are moving. If not, please let me know. So when you have the crystalline solid, you can think about close packing. It can be one dimensional, two dimensional, or three dimensional. In one dimensional, what is the way you do it? It is only one way you arrange those spheres in one dimensional closed pack. That means they will be touching each other, and therefore, if you look at it, that each sphere has two neighbors. That's why quadrant number is 2. On the other hand, in two-dimensional closed packing, you can have square closed packing or hexagonal. In square closed packing, that is what we are doing. We are looking at this figure. You can see I have first row, second row, and third row. If I choose the middle of the first row as 1 and then 2, 3, 4, I can see that this is basically giving me a square representation. Therefore, looking at this middle one, it has 4 neighbors and quadrant number is 4. On the other hand, these layers 1, 2, 3, top, middle and lower are same type. That's why we call it AAA type arrangement. On the other hand, when you have the hexagonal type of stuff, you find that you have this 4 and then 3 then 2. And if I look at the connectivity 1, 2, 3, 4, 5 and 6, then it is a hexagon. So in this case, what is happening, that top layer, if it is A type, then second layer is a B type. And therefore this arrangement is AB type. Okay. So this type of arrangement has 6 levels. Again, I look at the middle one, I see there are 6 levels. That's why the quadrant number is 6. In three-dimensional case, which you are familiar with, we have hexagonal closed packing or cubic closed packing. Because we are just translating two-dimensional to three-dimensional. That means if I have the planarity, now we are adding the 3 axes. There are 2 types of three-dimensional closed packing. One is body-centered and one is simple cubic arrangement. Okay. So in this particular case, you have the square type or hexagonal type, right? In hexagonal, that means we are looking at layer A and layer B, and here again, if you look at on the left hand side, is A, B, A, B. So this is ABAB type, and it has a 6-fold symmetry because it is a hexagon, and it is surrounded, each atom is surrounded by 12 another atoms, 6 on one layer and 3 above and 3 below. You can see that, right? 6 here and 3 here, 3 here. And probably you have heard that occupancy is 74%. That means in this particular case, 26% is empty. And this is the maximum we can get. So in closed packing, we have to arrange inside so that will occupy the maximum space. And what are the examples? These are the metals that come into this hexagonal ACE. Similarly, in cubic closed pack, that also is called base-centered cubic. What we have here, we actually have A, C, and B, and A. That means we have AC type of stuff, but we can say A, B, C, we go from bottom to top, and again A, B, C. In this particular case, of course, you have a cubic symmetry, and therefore, in this particular case, the 12 nearest neighbors are there, quadrant number is 12. Once again, you have 74% available space occupied and 26% empty. And these are the examples that gives you this type of stuff, CCP. Now, body-centered is where you can find that we have the atoms occupy corners of a cube with an atom at its center. You will have a little bit more about this drawing when I have a cubic. And in this particular case, the quadrant number is 8, and you can see 68% is total volume, and therefore 20%. Therefore you have 32% space. And in this case, you have sodium, potassium, cesium, rubidium, and all these. And interestingly, only 20% of the metallic elements found to cause BCC arrangement. Okay. I hope you can still see me. I have a power card, but the laptop is working. Okay. Now, simple cubic arrangement would be such that it is going to give you a central sphere surrounded by 4 other spheres in 2 dimensions, so in 3 dimensions it is 6 spheres. Now, if I can summarize this, HCP, CCP or FCC and BCC, you can see that except the BCC, both are closed back, and the type of backing AB, ABC, AB is there, and efficiency 74%, 68%, and 12, and 8. Okay? So this is kind of a brief introduction to the solid, and I just wanted to remind all of you, those who would read a book before, say, 1990, you see that the carbon had this diamond and graphite. Then came this carbon nanotube, then Maki was C60, and that graphene, which gave a Nobel Prize in 2010. That means the different forms of carbon are shown on this slide. When we studied, we only knew about these two. Then in 87, all this story came, right? Now, finally, in this solid part, I have to tell you a little bit more. What it is? That ionic compounds. We know that AB and AB2 type of are there, and what are the AB? For example, sodium chloride, sodium chloride, zinc sulfide, there are the three. We call it rock salt, we call it sodium chloride type, and zinc blende. Right? In rock salt, as you know that we have the cube, and you can see that the chloride ions are at the corner, and sodium ion is in the middle of this. And in this case, what happens that sodium ion occupy all the tetrahedral side, that is body center and base center, and this sodium ion is surrounded by 6 chlorine, and similarly this chloride is surrounded by 6 sodium ion. Right? Therefore, coordination number again 6 and 6. So we call it 6. But interestingly, if you apply pressure, then the sodium chloride structure goes to sodium chloride structure, which I will talk next with 8 to 8 conversion. And here, of course, lithium, sodium, potassium halides, and silver chloride, silver bromide, calcium oxide gives you this structure. Now, if you go to sodium chloride, what happens here? You find sodium is in the center, and therefore you have 8 chloride surrounding sodium ion, and vice versa. Each chloride is surrounded by 8 sodium ion. That's why quadrant number 8. So in this case, it is actually body center. And as we are speaking, that means in addition to sodium chloride, we have sodium bromide, sodium iodide, and so on and so forth in this category. And zinc sulfide, you know that it has sulfide as well as zinc, and here quadrant number is 4 and 4, because each zinc is separately surrounded by 4 sulfide and vice versa. And interestingly, copper chloride, copper bromide, and others are in this category. And therefore, this gives you some idea about AB. Now, AB2, I must talk because calcium chloride, which I call chloride type of structure, there again you have the chloride ion occupy all tetrahedral bites, and this calcium is surrounded by 8 chloride. That means here the number of calcium is 8 and chloride is 4. So calcium chloride structure has 8 to 4 quotient number, and these are the examples other than calcium chloride. So that background of solid is very important because we are dealing with solid. I hope that all of you got this information, which is not unknown. It is to some extent known to you, and senior members may find it very rudimentary, but I have to do it. Okay. So next, I am going to go that we are talking about X-ray. So what is X-ray? How it was discovered? I am going to go one by one. We just talked about solid. Now we are going to talk about X-ray. Now here, X-ray was discovered by Roentgen in 1895 when he was dealing with some cathode rays for studying some luminescence property. And with this discovery, he actually got the first medical X-ray of his wife's hand in that year. And interesting enough, he got Nobel Prize, first Nobel Prize in physics, and he attended the Nobel talk, but he did not give the talk. Okay, so this is over 120 years, 25 years that we are 30 years we are talking about. But it was not clear in those days that what is X-ray? Is it electromagnetic radiation or another form of light? And then many other experiments have been done. And interesting enough, this experiment by Arnold Sommerfeld with single slit experiment finally shows that X-ray had wavelength about 1 angstrom that I mentioned. And of course, you cannot deny without the involvement of Albert Einstein, because in 1905, when he gave the concept of photon, Arthur Compton says that X-rays are not only waves of electromagnetic radiation, but also exhibit particle-like properties by the scattering of X-rays on the electron. And this is the basis. That means X-ray is interacting with the electrons in our elements, compounds, and that's why you are having some interaction. Using that information, in 1912, for the first time, we had that X-ray diffraction work by Bragg and other people. Okay. Now, you know that X-ray is generated using a vacuum tube. So here I am showing you on the right hand side that here is the X-ray tube where you have the cathode, okay, and then you have an anode. And this cathode is charged with high voltage AC current, right? And then that bombards the electron on the anode, and that generates the X-ray. The anode is heated up because of this bombardment. That's why we have to have a cooling system, normally water, that circulates and cools this copper. But interesting enough that if I can rotate this anode, then the dissipation of energy would not require you to limit the X-ray to 1.8 to 3 kilowatt, rather you can go to 9 to 18 kilowatt. Why it is important? Because if I have this crystal and if I have very powerful X-ray, then I would get diffraction, right? So this rotating anode was there from 1983. Rigaku was the first one to operate with the radio detector. But in India, there is no small molecule single crystal with rotating anode because its maintenance is different. Now, with technology improvement, we don't need any more circulation of this water. It can be air cooled because it is a problem. So here you can see rotating anode is spun around about 6,000 RPM to take care of this grid generator because this is very powerful. And in this particular case, what you see that we have already a window through which X-rays are coming and we use this. Okay, so this X-ray tube, little bit further we can talk about, because everybody talks about is X-ray having exposure when you use a diffractometer. It is not, because two things. One, the opening of the radium window is controlled by a solenoid, and this solenoid would be controlling that. Suppose you have the X-ray on and you try to open the door of the diffractometer, it is going to shut off. Similarly, as you will see in few minutes, that diffractometers come with a glass window, and that glass has lead footage, so no X-ray comes. And the safety matter. In other countries, nobody can bypass this kind of stuff. In India, some engineers they try to do manipulate, but in either Monali it doesn't happen. All right. Now, two more things about what I said, that we have some optics. That means I am generating my X-ray, but I want that X-ray should be monochromatic. That means single wavelength. For example, here we have moly as the anode. I showed you example is copper, so we have moly, K alpha and K beta. Two types of radiation can come, and here I am interested in moly K alpha because this should be monochromatic. So interesting enough, if I use some kind of filter, and normally that filter is one below the atomic number, but when you go to group second row Benson element, then it is 2 n minus 2. So zirconium does the job. So we gave this alpha just putting a filter, Similarly, you can also use a monochromator that can help you. Monochromator can be diamond or graphite, that kind of monochromator to take care of it. Finally, when X-ray is coming, you have to have some sort of reduction in dispersion. So we have X-ray coming here and we want to have this X-ray focus on my sample. So we use something called collimator. And that collimator is about 0.5 millimeter diameter and it does the job. You can have 0.3 all the way to 1 millimeter, that collimator is available, but 0.3 or 0.5 are very common. Okay? Now, finally, X-ray source depends on the anode. So if it is chromium, your K alpha average will be 2.29 angstrom. If your iron is 1.93, if it is copper 1.54, and moly 0.71. As you decrease the wavelength, that means in case of moly, to find resolution is the best, that means it is 0.35. We'll talk about that resolution later on, why it is important. Because if I use manganese, if I use iron as the anode, then CH bond is about 0.95 angstrom. I cannot really distinguish the CH bond. In case of copper, it is still fine because we hardly have any bond below 0.75. You know, NH, OH, we consider that is there. So therefore, in this particular case, we get all these different kinds of anode. And right now, copper and moly are the most common, and chromium is also used. Many other elements are there. And by the way, if you have synchrotron radiation, you get much higher flux, and there the wavelength will be below these wavelengths that I am showing. It can be as low as 0.35 angstrom, and it does help if you have weaker crystal and you need to collect faster, right? So now with X-ray generation and the property, I'll show you the instrument that we have here in Hyderabad. Okay. First of all, in Hyderabad we have this Bruker diffractometer that you would not find anymore because this is bought in 2009, and first one was in Hyderabad, second one was in Hyderabad, and it was installed in March of 2010. And this diffractometer, as you can see, it is called kappa, full circle diffractometer with CCD detector. So here is the standalone unit. This is the chiller for the detector, and then on the back side you have the batteries, and then you have right there you have the UPS. So the area that is required for a diffractometer is not much. And in other countries, since they don't need any UPS and batteries, it is just a diffractometer. Here in close view, you can see this is my X-ray tube, and then the optics comes, and this is the collimator, and here is the goniometer, and here is the goniometer head where we have the crystal, and this is the detector. What is this one? This is the low temperature device that can give you temperature from 100K to 500K using liquid nitrogen. We use a Oxford drive system. And in this particular case, you have a camera because you need to center this crystal with this camera. Okay. So a lot of things are written here at the top, but I just summarize for you. And in this particular case, we are using this diffractometer now 14 years, and in between there is some issue. What it is that we cannot have any kind of replacement of this. We can buy the tube, no problem, but we don't have any beyond 15 years any supply of that. I take care of it. In fact, when Bruker engineer could not do, I did that kind of stuff, and it is working. Now, anytime you do a sample, you would say, what is the size of crystal? Normally, it is 0.1 to 0.5 millimeter size. Nowadays, with better X-ray source, we can go as low as 0.22. And shape should be, of course, single crystal, vertical is better. But I have given you some example here on the right hand side. This is very good crystal, this is not bad. These are marginal. These are stacked in place. If we take one, we can use it. This is marginal. This is also good, but this is along one axis you have that growth. And how you mount it? You can take a pin and you put a glue. You can put some nylon loop, which is very common. You can use a capillary here inside, right? That is there, and this particular one we put it here. So this is my concentrator A, where I put this crystal, and then I have X, Y, and Z. Z is in this direction, X, Y, we can manipulate. And we use a brass pin because if you use loaded metal device, brass will not have any concern. That's why there will be no movement. If you have even 0.01 millimeter change, that's a problem. So what do we do? We have this external coming. We have to center this crystal using that camera, and then we have a detector at which the angle, and then there is a beam capture directly there, right? So similarly, in powder, we have from Rigaku, this is made by Rigaku Japan, and this is also stand-alone unit. And here, if you look at it, that we have the extra tube here. Here is the sample stage, and these are optics. This is also optics and detector inspection. Unlike single crystal, where the sample that volumeter gate moves, X-ray is constant and detector is moving. In this case, the X-ray tube moves and detector moves, but sample is constant. And here we operate at 3 to our maxima with this voltage and current, and copper is the anode, and we have different type of sample holders. We can show you that in a minute right here. Top, that means in this sample holder I fill at the top. Usually need about 30 milligram of this sample. You can also backfill with the tape. You can put in a capillary. You can have this stuff in oil loop, or if you have airtight material, you can do that. We also do variable temperature, that means the setup is different. Okay, so this is how you can think about it. I hope that all of you are seeing what I am showing and listening to me. If there is any problem, please tell me. Okay. Prashanto?
It's okay, Sanjay.
Everything?
Will you please define 2 theta angle?
I
Okay. Okay.
So, because whenever you have a sample, you need to really know what you are doing. Now, to grow the crystals, also I took this opportunity to show you one of the methods is solvent diffusion. That means you actually dissolve your compound in a solvent and layer with another solvent. Criteria being that top and bottom solvent are visible, but your compound is insoluble in the top solvent. So at the interface you get. More sophisticated stuff is this one, where you have your solution of your compound and you put some hole right here at the test tube, and then you put in a beaker with some covering, and you put the solvent, which people call anti-solvent. I don't like that word, but people use it. It is because anti-solvent means that your compound is insoluble. So this vapor of this comes here. What does it mean? That means the boiling point of this anti-solvent should be lower than the boiling point of the solvent. So that vapor comes here and it gives you crystal. And here is one example of that. Other method is very well known in organic chemistry. We have a solution, we evaporate, and this is nothing but decreasing the solubility. When you evaporate, we do solvent, therefore your supersaturation comes, and that is there. And solvent apparatus is very sophisticated stuff. I'm not going to talk about it. It's a different story for the sake of it. And these other methods are also very sophisticated. One of them is sublimation. That means you have a sample, you heat it, you have a cold head, and you cool vacuum, you get a good crystal. Similarly, convection can give you have a sample here, you heat it, and then you pull it here, and you get that crystal deposited right here. The other method that also are used, like pulling. If you have a saturated solution, you pull it, because there again you get for the lowering, you get the solubility less, and therefore this is how we grow crystals. And now comes the basics of crystallography, right? And this is the part I will try to do in 10 minutes or less, because this is a compression of a lot of stuff. And in order to talk about it, we have to talk a little bit of symmetry. And you know that those who have seen a cut of bull or cow, you have this, right? You have 1, 2, 3, 4. That means 45-degree angle. If you rotate, you get the same. And those who are picture lovers, They'll say, yeah, I get 8 slices of pizza, and this is how you cut one pizza into 8 slices. So the beauty of that cut wheel is that 45-degree angle gives you this idea of symmetry. Now, symmetry is nothing but repetition of a pattern when I apply a symmetric operation. For example, if I have inversion center that is sitting here, I get to see that this is generating this, right? In a molecular level, you can have the inversion center here, and then you see this carbon which is up is now down, and so on and so forth, right? So one of the symmetry element is inversion center. Mirror plane. Here I have shown one gypsum. At the x plane is the mirror plane, and you can see that this side and that side can be reproduced. Similarly, in molecular level, if you have a mirror plane like this, molecule A and B gives you this reflection, and therefore it is a mirror plane different axis. Look at an axis. If you have a scissors, you can see that two-fold axis right here. Similarly, if you have a parallelogram, you can have a two-fold axis, and that is the symbol that we use in crystallography, that this is the sign of two-fold axis. Okay? And then, using many other symmetry, we look at the point group. So there are 32 point groups that are used in crystallography. And out of that, 21 of them do not have center of symmetry, and 11 of them have center of symmetry. Center of symmetry means you have inversion center. And out of 21, you have fused electric, that means 20 point groups are there, and one is non-piezo. And out of 20, you have 10 which are polar and piezoelectric, and then you have only ferroelectric. And why this part is important? Because some physicists they want to study piezoelectric. That means or compound has to have no center of symmetry to get the piezoelectric. And then if you want to go there further and piezoelectric, then you have to choose that. Right? Now, going back to the road, if I have repetition of these points, right, in y-axis direction, I have this. And if I say this is the b-axis, because it is y, and length is between these two, that is my one-dimensional lattice. Now, if I convert that into two-dimensional, that means I add that x-axis along this, we have that distance a, then the angle between a and b is gamma. That means I have a green stack of rows that is green. If I look at the pattern, that means I can have this B and A as the right angle, or I can have this A and B that is giving you also kind of area with gamma. On the other hand, if I now add the z axis, that means I already showed you two-dimensional, and I'm adding the z axis, that is the c axis. On the right hand side, you can see that this is the c axis, this is the b axis, this is the a axis, and the relationship of a, b, c with alpha, beta, gamma are shown here. That means the angle alpha generated with b and c. This is very important because this is where we are going to use 6 parameters, a, b, c, and alpha, beta, gamma in three-dimensional structures. Right? Using that, simply we have the conditions. For example, when I have A, B, C, all equal, alpha, beta, gamma, all 90 degrees, that is a cubic system, and there are Bravais lattices which I will tell you in a minute. And then tetragonal means I now lose 1 degree of freedom. That means my AB are equal, but is not equal to C. If I go further, I can see that alpha, beta, gamma, all are 90 tetragonal, but in the hexagonal I can make it gamma 120. Rhombohedral is typical of that hexagonal, but it is not 129. Then orthorhombic, what is the condition? Alpha, beta, gamma 90, ABC are different, and then if you go further, ABC are different, and beta is non-90, alpha and gamma there. When I have no relationship here, that means I have highest degree of freedom. ABC and alpha, beta, gamma all are different, that is the trichromacy. That means I have these crystal systems, and I have these Bravais lattices putting on them, and the condition that comes because of this, right? So, when you solve the structure, what do you think? You have a crystal. If I go back, just like electrosynthesis, I see that this box here in a crystal is a lattice. Each lattice has unit cell and each unit cell has asymmetry. In this case, this unit cell has two asymmetric units. So if I can solve the structure of this asymmetric unit, then by definition, due to this symmetry here in vertical center or two-pole axis, whatever you want to do would give you that. That means by knowing the asymmetric unit structure, I can go to tell you what is there in a unit cell, that will tell you what is the lattice and the whole system. So idea would be to do that. In crystallography, in addition to the symmetry elements that you are familiar with, there are two things that to be understood, and this is based on translational symmetry. When we have talked about reflection and rotational, but in addition to that, we have translation. That means, in addition to reflection, if I first have the translation, that is what we call a live plane. In addition to rotation, if I have a translation, that is called screw axis. So these are the two terms, live plane and screw axis, that are new in this photography. And without translation, you cannot have any three-dimensional structure. And we already talked about this simple body center, test center. I just simply wanted to show you that this is simple cube, this is the body center, this is the test center, because each faces have a dark point. And putting provides lattices that I just talked about. That means primary cubic has cubic has primitive, test center, and body center. Orthonorm says David both. That's why they have it has primitive, body center, base center, as well as base center. And tetragon has two, P and I, body center, then operational hexagonal, and primitive and body center orthonomic are there, and in tri-trinity you have complete trinity. So this is how you need to understand a little bit about the Bravais lattices, because when you say that I got my unit cell in a tri-trinity, then you say, yeah, it is only primitive. But if it is monotrinity, that will be primitive or body center. That you will know a little bit later how to do that. Now, in crystallography, we have something called phase group. That means each crystal belongs to one phase group, and there are 230 of them. How do we generate these 230? If you already know that 7 crystal systems are there, we have put in Bravais lattices, and then we have 32 point groups. If I combine these 14 Bravais lattices and 32 point groups for 7 crystal systems and apply the new thing that is screw axis and light plane, I get 236. Okay? So this is unique. That means each crystal system has different. So here P1 bar, P1 by C, C2 by C, all these are examples of phase groups. And as I say that 230 phase groups are there. But out of 230, hardly even 30 are observed. But in some cases you find that 3-4 phase groups actually take more than 30% of the total crystal structure in the world, because that is most common. Okay. So all this talking keeps you wondering what is the origin of the structure. As I said that solid is having a periodic structure, as I have mentioned, and then that interacts with X-ray, and therefore electron in atom scatter light, and this scattering is depending on the number of electrons. That is the value of J. If I have more electrons, it will be scattering stronger. And the wavelength already we know that it is similar to the distance. That's why we are able to look at the pattern that gives you the data to get the X-ray arrangement within the crystal. Now many people ask, like, you are interested only in diffraction. X-ray is interacting with the crystal, solid, it is diffraction. That is not absorbed, that is not reflect, that is not refract, that is not transmit. Yes, it does, but we only can change that diffraction, and that is due to the fact that the Bragg's law. Okay, so I want to say that this definition of theta and 2 theta comes because of Bragg's law. So lambda is related to the sine theta, and theta is defined here. Here, when you have the incident beam and reflected beam, you have a vector A, and this angle is theta, that angle is right. So therefore, in this particular case, what we are looking at is that you have a lot of planes, and they are separated by DH, KL, and that is G. Here here, and we can actually get the information of HAL from the Miller indices. I'll give you an example. So in this particular case, what is happening, that the space between refracting planes of atoms determine the peak positions, and the intensity of course is determined by what atoms are refracting on the refracting plane. Because as I showed you that those which are interacting with X-ray and it has a proper angle like theta, that is Bragg's law has to be followed to observe that refracted beam. And this is where Bragg and Bragg did it, and some of you would be wondering that he was doing summer project with his father and contributed to create Nobel Prize. He's one of the youngest Nobel laureates in the world, right? Let's move forward, and I'm giving you some example that if I have one zero plane, that means my cut at x-axis is A1, and then that is parallel to B and C, right? You can see that this is my x-axis, so the cut is here. So these two planes are parallel to each other at 1 on the intercept of that. Similarly, 100 means that it is having intercept of 1 on A and B, but it is parallel to C. This is how it is shown here, that you look at that you have intercept from origin to B1, and then you have intercept from origin to A axis, this one, but this is parallel. So we are talking about the middle one, this is the front, this is the back, these are all parallel planes. Many other examples are there, but we have to cut short. Before I move into further, I just wanted to tell you that when we take a diffraction pattern, we get to see like this, and in this particular case, what we observe, we actually observe the points. That means we are getting a point in the reciprocal phase. Why? If you mathematically think, reciprocal of a plane is a point and vice versa. So we actually get the Miller in this case, that is a plane based on these diffracted points. Okay, these points are being coming into the real crystal system. That means when we collect the data, we get the diffraction pattern in reciprocal system. And this is a little bit confusing, but trust me, if you just understand a point is the reciprocal of the plane and vice versa. Here you see that 110 is shown without the parenthesis. That means if you have the parenthesis at the plane, then you have 110 at the point, just like your XYZ dot in your thing. Now I talked about resolution, that point 35.71 and that kind of stuff. So when your crystal and you have, and if it doesn't have enough resolution, you cannot do anything. Here we have this compound crystal, and I'm going to tell you that if you have the crystal very weak, suppose if you cut at 4.5 angstrom resolution, you see nothing. Until you move all the way to 0.83, you see that I can see the density of the hexagonal system. That means I have the benzene ring here with benzene substrate with 2 nitrogen. So you can see all the molecules, water, then you have the diamine and the other compound right here. So in other words, that if I have a crystal, it doesn't refract at 0.83 angstrom, I cannot solve the structure. And this is the standard from the international union of crystallography. Okay, so I can collect data at 1 angstrom if your crystal is weak, but I will not have very good idea about carbon hydrogen bond, because carbon hydrogen bond will be 0.95, my resolution is 1 angstrom. So I will not be able to see that, right? So in powder, we see only kind of rings. I will be going through this very fast because this is very difficult to understand. But what I say that powder is mixture of so many single crystals. So they are overlapping, and that's why they are giving you a ring, not a single spot like single crystal. Now, after saying all this stuff, one would say, what is the use of single crystal experiment? Of course, first use is we want to know the 3D structure of the compound. More importantly, we want to know the chirality around the center, because no other method can give you the chirality of the center other than single crystal diffraction. Then we also want to know what kind of supramolecular interaction is there, hydrogen bonding, fiber interaction, any other interaction that is up there. Polymorphism is something that means one compound which exists in two different forms due to some sudden changes in the dihedral angle, and we can also determine that. And then the charge density and bond. Charge density is that we assume that you have this bond where electrons are shared and they are in between. But if you take the example of kerosene, where we draw that iron is connected to all 5 carbon of the CP charge density data has shown that it is not true, it is actually 3 of the 5 which are much closer or having that different density. That is, some study purely, crystallography, very few people do it, it is not easy to do, and you need to collect a lot of data. So, I am just showing you that we get the crystal structure of this manganese paddle structure. It is 3-dimensional, that means I have this paddle wheel pointing in this direction, and then this lead card for vibrating is connected. So this is showing you that it is a 3D structure. Similarly, this is also some metallic remark with force. Similarly, this pattern, beautiful pattern, means you can have on the cloth which will give you this. These are real compounds, by the way. We have solved the structure and did this. Now, hydrogen bonding is important, and here these green lines are showing that hydrogen bonding between base, carboxylate, oxygen, and the continental water, and many other things are there. This particular hydrogen bonded metallic thermal, the magnesium system, cross system, is connected by hydrogen bonds. Similarly, another example would be that I have a lot of land water, and that are hydrogen bonded with the carboxylate and other moieties. And last year, you see that here is a aqua species, that means diamond of water. Both hydrogen on each water is connected to this carboxylate oxygen. So you have a repeat of this right here between this carboxylate dimer of a manganese compound. Okay. Now finally, fiber interaction can be also looked at based on the 3D structure. Normally, if you have between 3.3 angstrom to about 3.9 angstrom between the rings, then that is valid. Okay, so we would be able to determine the 3D structure and all this stuff. What is the use of powder exactly? In case of powder, we can understand whether my material is single phase, means phase pure. We can also look at the polymorphism. I will give you an example that if I have 2 polymorphs, their fingerprint, that is powder exactly would be different. That's how you can also see. Then degree of crystallinity, and that is the great point for pharmaceutical industry. That is the last part of my talk, where the degree of crystallinity has to be about 95 to 97%. So we can tell you whether your material is 100% crystalline or not. And then you can monitor any type of application. For example, I am talking about catalysis. That means before catalysis, I can take powder exactly of the catalyst, and then after catalysis, I can take the powder exactly of the catalyst. And if they match, that means my catalyst is intact. I can recycle, I can prove it that it is robust. So if you do fluorescence, same thing, that before and after fluorescence. If you do any kind of gas absorption, if you do any other application, powder exactly is going to tell you that the recyclability and robustness of your material. Last what I have said here is isostructural, isomorphous nature. How do you know that 2 compounds are isostructural? And I'll give you those examples matching their pH. All of you know that titanium dioxide exists in 3 different phases, anatase, butyl, and butyl. But their pattern is different as color potential. Anatase is most common, and this TiO2 is in your type of water, by the way, and Johnson and Johnson is in trouble. So the type of water used has come down. In this particular case, so if you have an unknown sample, you can find out whether it is 100% anatase or 100% butyl or 100% butyl, or you can tell whether this mixture has this percent, this percent, this percent. Second example is SiO2. There are 3 phases in glass which is amorphous, but Crystalline form of exercise exists in two ways. One is quad and one is crystalline. Why quad and crystalline has different patterns? Because their structure, if you look at it, within the unit cell is different. That means arrangement of that SI unit in the three-dimensional structure is clearly different in quad and crystalline. That's why they have different order exciting pattern. Right? This is how you can say, is it a polymer? Yes, it is. Now, side effect. You work with nanomaterial, you see most of the time with a lot of broad peak. That means you have 2.5 nanometer all the way to 4 protein. When you go up in the size, you see soft bits. And this is because of solid equation you can use and calculate all this stuff. And here, that means to make your order sample, you should not grind too much so that particle size goes low and you have order pattern than you want to expect the subject. Okay? So this is the science effect in case study. As I say, case theory. I made a compound via hydrothermal or a flux condition. How do I know they are the same? Just simply doing the pH study, you see, it is matching. And then I have a crystal structure of the compound. That means crystal and the two methods that I have used in hydrothermal analysis, I get the same compound based on this comparison of orders. So it is very powerful to tell that it is not just a crystal structure again, my whole compound represented by the crystal. And isostructure which I told you that compound 1, 2, 3, if you look at their power pattern, they are matching. That means if I do the crystal structure of 1, I really don't need to do 2 and 3. We did it. We have the simulated pattern that is from the single crystal data, and this is the experimental. But without doing the single structure of 2 and 3, I could say that whatever is the structure of 1 and 2 and 3, they are the same. Only difference in these compounds are the carboxylate spacer. That means I have chosen oxalate, I have chosen succinate, and I have chosen malate. Right? So that's how it is there. And the last story I have to be told about this order pattern with sodium chloride and potassium. You see, potassium is larger in size, but they are in the same crystal system. So if you look at it, for potassium chloride, this peak has shifted to the left on 2 theta scale because already intensity versus 2 theta. So they are the same pattern, but it is shifted to the left because of the size of potassium. That's all. So are the isostructure? Yes, that is correct, right? Now, Prasanto, this section would take me about 20 minutes.
Yes.
Should I continue?
Yes, sure, no problem.
Okay. So, I hope that you got a lot of information today, starting with the property of the solid. And then I will give you some information about how X-ray was discovered, how X-ray is generated, and I briefly talked about the instruments. I also talked about what kind of sample required, how you give those samples. Then I gave you some idea very briefly about the theory of diffraction, and then I gave you what are the uses of that. But this particular field, pharmaceutical industry, dive for taking the order pattern, because here you need to really make batch to batch or multiple sites drug exactly the same. So they use the order pattern to match it. Okay. So that's why I spent about 20 minutes to tell you the importance of order is diffraction in pharmaceutical industry. And before I start, what is the background here? Background is there are the biopharmaceutics classification system, BCS, and you can see that class 1, class 2, class 3, class 4. They are high permeability, high solubility, high permeability, low solubility, the low permeability, low solubility, high solubility, and low and low. These are the drugs. Some of them are for blood pressure. So, since 85% of the drugs are used as solid, we actually depend on the solubility and permeability. And these particular things, class 2 and class 4, are the trouble. So, what people are doing, people are trying to increase that solubility and permeability by co-crystallizing with the drug and increasing the efficiency. But how do you know that you are not disturbing the original active pharmaceutical ingredients provided? So powder exactly actually does that job because if you have to measure that, right? So in other words, we already talked crystalline solid can be amorphous or single component, multi component, and then you can have hydrate, that means that is there with water, then you can have salt, you can have solvents, that means they are other than water, your other solvent, and you can have co-crystal. And both single component and multi component can give you polymer. Pictorially, I am showing here that when you have neutral compound, you can have monomer, you can have hydrate and solvent, you can have the co-crystal, and you can have co-crystal hydrate. And these are the keys. This is active pharmaceutical ingredient and water solvent, neutral gas, and counter ion. If you have the salt, you have this kind of arrangement. Then you can have hydrate or solvent because I am inserting that triangle here, right here, and then salt co-crystal, that means you have another component there, and of course you can have salt hydrate. Right? Why it is important? You see, drugs sold in the world, hydrochloride salt is the most common. Hydrochloride is the in case of cat and sodium is the king. But when you have high blood pressure, you cannot use sodium, that's why calcium, potassium are used. All the cholesterol lowering drugs, they have the calcium, not sodium, because when you have cholesterol, you also have problem with your blood pressure. So here, the anions and cations, they create that co-crystal salt, right? So what is the key industry requirement here? That you have to have 90% of pharmaceutical products contain active ingredients and they are in crystalline form. So we have to make sure that the product that is required by the customer is meeting the specification. What is the specification? We have a powder pattern that this is what I want. You make multiple times, you scale it up, you make in different places, but you have to meet that. If you don't meet it, then they are going to reject and it is going to create a problem in losing money. You have to redo all this stuff. Right? So I'll show you about 4-5 examples and finish my talk that way. Okay? So here you see that this is intrapronatal, this is a fungicide medicine. Right? This is the structure of that intrapronatal and the powder pattern shows that it is crystalline. Right? Here we have the intensity versus lucida, which is about say 2 degree all the way to 40 degree all these patterns. And this is unique for this compound. Now when you have amorphous tetragonal, same drug, you get this kind of pattern. And if you get this, they are not going to accept it, you need to have this. So if you have amorphous material, how do you make crystalline? That is that process can come into play. So using a drug called pyrrolidine, we have this study where you see that first you had that, amorphous to broad peaks. Then after drying an ambient condition, on the 7th day, you see that it became crystalline. That means we are able to get rid of some of the solvents in it due to drying, even ambient conditions like that. So we can follow it by PXRT that as we are 2 days, 3 days, 5 days, then 7 days is good enough. So people should not be nervous that, oh my God, I made a drug and it is amorphous, but I need to meet the specification. So you need to spend time, such as decrystallization of that amorphous drug to get into this condition. Because without crystallization, it is not going to do anything in our body. Second example here is very interesting that you know sucrose. So if I have the powder pattern of 100% crystalline sucrose, this is there. I can also have 100% amorphous, that is the pattern of sucrose. Now I have pattern 20%, 40%, 60%, 80%. Now you give me one unknown sample and I will tell you what is your percent of crystalline. So using even sucrose, this is example. This is just like when you do the permanganate solution, beer numbers of plot. And when you are given one unknown, and you say, yeah, in this plot, I can see where is the point. And this is the key in industry that I have to have 95 to 97% crystalline drug. So can I have that through the PXI development? And sucrose is the example I have used here, and you can see that it is very similar how you can do quantitative analysis of crystalline of the materials of the sucrose. Similarly, you can have one crystalline material, and then over time you make it amorphous. It's a very apprentice compound. When we have this material crystalline, somebody was grinding and grinding, trial grinding. Due to this grinding, what happens in 90 minutes it became this. So people think that if I have cryo grinding, I can have better job. But in this particular case, there's a wrong method to choose. Right? So this particular drug, piroxicam, shown here, has been utilized to give you an example that I go from 100% crystalline to amorphous material. Just cryo grinding over 90 minutes. So people have been learning lessons that some of the methods are not correct in some cases. Okay. Then comes that, when we put a drug, we have many components, and one of the components is this PVP, okay? That is the coating. So what we are showing here, that 70% PVP, 90% ferrolipine I talked about, and therefore you see that when this 30% ferrolipine and 70% PVP have been together, and this amorphous ferrolipine is right here, it looks like that the ferrolipine 30% in PVP is similar to the amorphous ferrolipine. So making a drug in a form of tablet or form of capsule is not easy. There are many drugs which actually fail to give you that. So this myth that I have discovered a drug and it is going to cure all this stuff, even at the stage of not being able to make a tablet or supply as a capsule, in its crystalline form can jeopardize your drug delivery. Okay, so you cannot even, unless you make a tablet or capsule, you cannot do that. And suspensions are there. You know that suspensions for child, we have a suspension of antibiotics. We also have suspension for intramuscular or intravenous type of stuff. Those are the other solid method delivery systems that we talk about. But there again, you have to see whether crystalline is right. Now, this particular example I am choosing because I talked about that polymorph. So this sulfapyrazine is used in getting a sulfur drug, marvelous drug. You can see that it exists in two different forms. We call it polymorph. If you look at it, this is form 1, this is form 2. Here this peak is not there, this peak is not here. Then if you look at that, this peak is there, but that peak is not there. So this is unique. That means its crystallization, that is backing, just like SiO2 I showed you, is such that it has different pixels. Why it is important? Because some drugs in one particular polymorph form is active, not the other way around. Okay? Naproxen, for example, was sold as a mixture of R and S, and we found after a long time that the S that is active, R is not. That means in the very beginning, they are giving you 50% active material. R and S will have two different pixels. So now, nobody can sell you R and S mixture. They have to sell you S because R is active. We also know about methyl dopa, that is another blood vessel body. Okay. Last three slides are our contribution in this domain. One is polyethylene sartan. It's a hypertension drug. I mean, I would say that probably 50% people in India they take this drug, Telma 80, Telma 40, Telma sartan. So, with collaboration with Professor Chara and PU, what we have done, we have co-crystallized saccharin, and we find that its solubility goes up 9-fold, while the efficacy goes up 2-fold. Without increasing any toxicity, because saccharin is not a problem. And here you can see the systolic pressure measurement on a lab. Okay, and some of you may know that systolic is the upper number and diastolic is the lower number. Normally 125, 180 people say is a good number, and we have shown that control versus tell me with the saccharide is the best right here. So this contribution actually helped to get a patent, and basically it is going further to look at how saccharine is then started to be there. Next one is hydrochlorothiazide. Again, this is a hypertension drug, we call it water pill. When you have Telma H, you know Telma H is hydrochlorothiazide. Here again, we have co-crystallized with nicotinic acid, and it gives you threefold increase in solubility. Remember, I told you with the solubility, permeability, there's a key, and we are able to increase 1.5-fold efficacy. Toxicity, yes, nicotinic acid may have, but it is not that difficult to believe. And here again, we have shown you based on the systolic pressure, and there you see that ACTNA it has the highest and number of days that is there. Last example actually is so important. Lamotrigine, it's the only drug for epilepsy. Okay, this is the only drug. Here again, this was obviously in 2013. I tell you, when I got involved, I was very emotional because epilepsy is a serious disease. It's a seizure, right? So what we have done here with lamotrigine, we co-crystallize acetic acid, propionic acid, sorbic acid, or glutaric acid. And here we are showing the structure of the drug and glutaric acid. And you can see that if I have lamotrigine powder XRD and then I have glutaric acid powder XRD, then you can find that compound 6, compound 7, compound 8, compound 9 in this order: acetic acid, propionic acid, sorbic acid. That means compound 9 is my glutaric acid, that is shown on the left hand side. Is basically different from glutaric acid as well as it. Right? That means this particular one, we have certain peaks that may be common. This particular crystalline material on the co-crystal has been 4 times more soluble. Okay, so that's why we have been able to contribute to that. We have talked about a little bit on patenting based on the EXRD to some extent, because when you have a patent, you have to show that which polymer I don't hold that. So EXRD would be included in the patent, that this is the material that I am patenting on. But somebody else can come and say, no, your material is form 1, my material is form 2, so I am not infringing your patent. So intellectual property consideration is very important when you are involved in this. So therefore, in this particular case, you have to give the listing of physica and the intensity of the material you are patenting on. When you have the polymorphism, then there again you need to claim that I have 2, 3, 4 forms, and I know exactly what are the EXRD, and this is included in the patent. So nobody can come, make the same material, and say, yeah, you have patented this for this drug, and this is for polymorph 1, but other 2 you have not patented. But if you included that, nobody can touch your compound. Okay. Similarly, I gave you examples of different salts for crystals. There again, when we patented, we had to give that, look at. Here are the PSC pattern. So not only satisfy the customer needs, where customer said, I need this pattern to say that you made our material, but also this PXRD is going to give you the intellectual property rights, and that is very important. Because nowadays, US patent is valid for 20 years, and sometimes to get the patent granted, it takes 5 to 6 to 9 years. That's why blockbuster drugs, they are very expensive, because unless they have $10 million income, they cannot cover the expenses. One drug development costs about $750 million, almost close to $1 billion, right? So if you have a patent, somebody wants to use your patent, you also can make money on it. And nowadays, a lot of people talk as a patent, but that is not a patent, that is not an application, invention disclosure, and then application, then review, and then gives you the granting of the patent. So in conclusion, today I talked almost 1 hour 15 minutes, And I want to tell you that I have gave you the success story in pharmaceutical industry where our excel is the gold standard and bioavailability improvement of API is done with solid format mitigation. Then the screening and selection of studies is very important. Some of the pharmaceutical companies, they have their own bench top or Excel, where they can screen hundreds of samples per day. In our department that I showed you, we work from 8 a.m. till even 2 a.m., 3 a.m. sometime, and we could do about 50 samples. It takes about half an hour to 20 minutes per sample. Single result takes, depending on the system, 4 to 6 hours. And then you can find out that intellectual property issue is very important, and therefore, if you have PSRD pattern in your patent application, then that covers you. I hope I have been not broad in our discussion, but gave you some idea about this and many other things I could talk, but I open now to answer if you have questions because that is more important for what you understand. Thank you.
Okay, thank you, Sanjay. So, it is a